Thank you very much. Good morning, everybody. So yeah, the talk is about how to ruin your business with machine learning and data science. A little background about myself. I used to be a data scientist for a long time, worked for different startups and various projects. And then I founded a big data analytics company, and that was acquired by RapidMiner 4 years ago. I'm still with RapidMiner and filled various roles, being a product manager, an engineering manager, and now I'm back to my roots, leading the internal analytics team at RapidMiner. So I have multiple perspectives on how analytics can go wrong. So RapidMiner as a data science platform has a lot of customers, and we have seen some of our customers making mistakes, pretty big mistakes with data science and machine learning. And also we learned a few things from ourselves when we made some mistakes, when some business results went to the negative side instead of the huge expectations on the benefits. So yeah, I will talk about a couple of these things. But first of all, let me do a super quick introduction about some of the basic terms I use. So you hear about this AI hype, artificial intelligence. So basically what it is, to its core, it's mimicking human behavior. So that's what AI is. A subset of that is machine learning, when we try to teach machines based on historical evidence, so based on some data. And the subset of that is deep learning. You may hear a lot of hype about that as well, which is pretty much a neural net, a complex neural net that is very effective in learning various problems, for example, image recognition. So these are the key terms, and when I talk about data science, that pretty much goes across all of these. When you try to put all of these things into a business context, and you try to solve a specific business problem with all of these tools. And obviously it also has non-technical parts when you need to make sure that you can achieve the business benefits at the end of the day. So how I typically talk about these topics is I try to walk through the audience on a specific data science project. And it's pretty hard to pick a topic that everybody can relate to. So if I would talk about churn in financials, then obviously some startup people or some people at telecom are not that interested. So I'm trying to pick a topic that everybody is interested in. So let's talk about aliens. Believe it or not, there is an amazing data set documented by the National UFO Reporting Center. I'm still shocked that such an organization exists, but it does. And this data set includes 80,000, let's stop for a moment, 80,000 UFO sightings in the United States. Go check it out yourself. It's an amazing data set with all kinds of descriptions on how people have seen those aliens and what they experienced. So let's try to analyze this data set as an example. Full disclosure, I have a distant family member in the Hungarian UFO Society in a leadership role. So you know, let's take it seriously. We are here to solve this problem for the UFO Society. Let's take it serious. So we try to understand the patterns, how aliens are visiting us. So how every data science project starts is you try to understand the data. So what does the data include? So you typically do a few charts in the beginning. So this is the number of sightings per year. As you see, it has been pretty low for a long time, and it picked up around 1993. Does anybody know what happened in 1993? Pardon? No, actually, the institution is very old, which is also shocking. Actually, 1993 is when the X-Files started, the TV series X-Files, you know, Scully and Mulder going against all these aliens. So yeah, if you are hired by the Hungarian UFO Society to understand this data set, then you need to make your conclusions. Okay, so when the X-Files started, aliens visit went up, so the only reasonable conclusion out of this is that aliens are fans of the X-Files. I mean, that's so obvious. If there would be a TV series about data scientists, I would totally watch it. So they must be interested in how Scully and Mulder are dealing with their buddies. So yeah, that's pretty good so far. So let's see when they show up. So day of the week, time of the day, where you see more orange is more activity, more UFO sightings. So as you can see, it's more typical towards the evening, and it's very high on Saturday nights. Again, conclusion, aliens work hard, party hard. They are very social beings. They visit us with our Saturday drinks, they talk to us. Yeah, so I think we are getting somewhere. So we are getting a better understanding of how aliens behave. Let's see when they show up in terms of the day of the year. There's a huge peak on 4th of July, and it's the United States. So July 4th is Independence Day in the US. So any conclusions here? Aliens love America. And fireworks, because also on New Year's Eve there is some peak. So yeah, it's pretty good so far. We understand how they behave when they come, what they prefer, they work, they like to party and socialize with us. So after you do the data understanding part of the project, you are set to go to do some predictive modeling. So you use machine learning, even deep learning if you wish, and try to predict when they will show up next. So probably the next project you will have is by the society is that let's predict when they will show up next. So maybe your model says that, hey, they will show up in Amsterdam with 30% probability next week. So all the society is buying flight tickets to Amsterdam to be there. I will stop here because it's getting stupid. But I want to highlight one thing is that in this whole project I did so far, we haven't made any critical data science mistakes. The only assumption, the only supposedly false assumption we had is that the aliens exist. And this data set contains real aliens visiting us and not just people being drunk. So that's quite disturbing that only with such a small false assumption we can get to completely false results. So yeah, what I want to talk about on a more serious note today, two different ways how you can pretty much screw up your data science and machine learning project. The two ways are confusing correlation and causation, which we have partially seen in this example already, and doing model validation in a wrong way that produces overly optimistic expectations on how it will perform in the real world. So let's start with correlation versus causation. And another example, which is a little more serious than aliens, is there is this generic statement that if there are more books at home, then the children's test marks are higher, so they perform better at school. So that's pretty well understood, so it's a pretty strong correlation. So almost 20 years ago, the Illinois governor decided, hey, let's distribute books to every kid in this state, and that will potentially increase their success in school. They will have probably much higher paying jobs, so they will pay more taxes. It's a win-win, right? So they are more successful, the state will collect more taxes 20 years from now, so it's a no-brainer. So he proposed this plan. It would cost $26 million a year, but hey, millions of people paying more taxes, it will probably be more than that. So it seemed like a good return on investment as they expected. However, another study showed that students had high marks independent of if they read the books or not. One thing is having the books, but if you read it or not, you had the same test marks. So it does not really seem to be a causational effect. It's a correlation for sure, but it's not causational. And we could say hey, we are smarter, and yeah, probably the originating cause is the parents being more aware of their children's need to learn, so they create an environment where they can learn, so they have books at home. So that's probably a more plausible causation. But let me highlight that this is just another idea I have, just another hypothesis. I cannot prove it. Also, he couldn't prove it. He was actually proven wrong with this. Actually, this governor was not the most successful one. He is currently in jail because of bribing. So it wasn't his only mistake. But we tend to believe, and I'm pretty sure that especially people in this room, we tend to believe that, hey, we are dealing with data, we are probably more, we are not as biased as others. So we are objective. There are many people who are making subjective conclusions. When they see correlations, they just make subjective conclusions. But we tend to believe that, hey, we are way more objective than others. There's something called a bias blind spot. So if you ask 100 people about are they more biased than average or less biased than average, everybody says, like 85% of them says that, hey, I'm more objective, I'm less biased. 14% says I'm average biased. There is only 1 out of 100 who says I'm more biased than average. Let me tell you one thing, exactly 50 of them are more biased than average. So I really admire that 1% actually, who is so self-reflective that they realize, hey, I'm biased, I'm subjective. So a lot of us believe that we are making objective decisions in our daily work, but it's actually not true. We have a lot of bias in those decisions, a lot of assumptions. Maybe many of them are true, but some of them may be wrong. So I always encourage people to double check their assumptions. So if you assume that your business is growing in a certain way, yeah, let's just check the numbers and be honest with yourself. Is it really going 50% or is it just 42? Because yeah, if you start to project 50% moving forward, at some point your investors and bosses will be angry at you. All right, so let's go into a little more detail and look into a specific data science exercise. So let's look into a data set. There's one which is pretty well known. Unfortunately, it's not very good to read from remote, I guess. But it's a Titanic data set. So it includes 1,400, the 1,400 passengers of the Titanic, and has attributes like survived or not. So that's a pretty important one. Passenger class, when they boarded the Titanic, age, number of parents on board, number of siblings, and so on. So a lot of these machine learning algorithms are demoed with this data set because it's pretty well understood. Everybody knows about the Titanic. So how you typically do it is you load the data set and you do some so-called cross-validation. I will talk about that in a moment. So you basically try to validate your model to figure out how accurate it will be. So you try to predict, will these people survive or not? So if there would be a Titanic 2, you could tell people, if somebody wants to board it, you could tell, hey, you have a 95% probability to die or 95% probability to survive. So when you run this simple, pretty basic analysis, turns out that you manage to predict this with 97% of accuracy. That's suspiciously high. So if you look into the data, what you are really predicting here, there is one attribute in that data set which shouldn't be there. And the one attribute that is at the end of it, which lifeboat you entered. That's not really something you know before when you board the Titanic. And obviously there's a very high correlation on being on a lifeboat and surviving. So you need to be very much aware of what your data includes. And if you see very high correlations between attributes, yeah, let's stop for a moment and realize, okay, is it something I will have in a real setting? When I put this model into production, will I have this lifeboat information? Of course not. So that's certainly not working. So kind of a quick summary of correlation causation. Always check for correlations before doing any analysis. So check what attributes are correlated. Maybe some of the attributes are perfectly correlated. That's always suspicious. Maybe it's a data error. Maybe it's something obvious. So you should just exclude those attributes from your analysis moving forward. Always think it through. What is the information that I will have at the point of prediction? When I really try to put this model in production, will I have all the data that I have now for modeling, or will I only have the subset of it? Pretty good example is there are some models where one of the input variables is some average activity in that month. You do not know it on the 5th day of the month what the average activity of that user will be. So there are all kinds of ways how you can make attributes like that go into your training data, and then you have no chance to put this model into production because simply the data is not there. And if you have a chance, then monitor your models, do A/B testing. So A/B testing is a way that group A of your users are seeing one model, the group B is seeing another model, and just observing their behavior, which one is performing better, then you can have a real distinction if this model is making a difference for your business or not. Then you can really prove real causation, because if the only difference of those two groups is the different predictive model that you put in production for those, then really that must be causing the difference in behavior. All right, and the second one is there are so many ways to make mistakes in how you validate your machine learning models. So let me bring you a few examples. By the way, these boxes are really just to represent how an analytics process looks like. So step by step, data flows in and out of those boxes. So let's take an example when we have completely random data that has some target attribute, which is binary, yes or no. Completely random data. You train a machine learning model on it, and you apply that model on the same data set. So if it's completely random data, what is your expectation of the error? Obviously, it cannot be better than 50%, but if you actually run this, error is 0%. It's absolutely perfect model. Yay, let's put it into production. No. So a lot of people are going crazy about this training error, so what the error of the model is on training data, but in most of the cases, it's completely meaningless. So what you need to do is really this technique called cross-validation. There are also other types, but cross-validation is by far the most popular and the easier to use. So what you do here basically is you split your data to multiple chunks, and for example, 4 chunks, and you use 3 chunks always for training, and the 4th one for testing. And you do it in multiple iterations. So basically, all of your data will become training data at some point and testing data at some point. And you make sure that whatever the model was trained on is never seen by the model in the testing phase. So all those data sets are completely independent. Then you can have a 50% correct estimation on how this model performs. Obviously, no matter how much hype there is around machine learning, I guarantee you that random data cannot be predicted better than 50%. And the stock market is a good example. All right, the other one, even if you believe you do perfect validation, I'm doing cross-validation, I'm good, but you put it into an optimization. So in many cases, what people do, hey, I have a model, it has 5 parameters or even 50 with some of the more modern models like deep learning, you have a lot of parameters to tune. So people start tuning it. Maybe I get better error or better performance from these machine learning models if I change those parameters. And just rerun and reiterate all the analytics and all the measurement of how well it will perform. And then report the best result. So let me bring you an example. Let's say we have 100 rows in our data set, 100 records, and again, a yes or no outcome that we are trying to predict. Let's make it if somebody is paying back their loan or if they are churning from some customer. That's a typical binary target. Let's put it into a black box model. At this point, we don't know anything about this model. It could be deep learning. It could be anything like that. The model has 3 parameters, 0.1, 2, 5, 1, and 2. Parameter 2 is yes or no. Parameter 3 is yes or no as well. So we have absolutely no understanding of this model, but let's just optimize its parameters. That's actually what many people do. They do not really understand the mathematical foundations of the model, but they just try to get more accuracy out of these systems. So let's say that the outcome is that parameter 1 should be 1, parameter 2 should be yes, and parameter 3 should be no, and this is predicting by 62%. All right, let me reveal what the model was. The model is Zoltán with a coin. I trademark it. So I just start tossing coins, and if it's head, I say yes. That's my prediction. If it's tails, I say no. And the 3 parameters, which euro coin I use, 10 cents, 20 cents, 50 cents, 1 euro, 2 euro, toss it with right hand or left hand, and do I wear glasses while I'm tossing this coin or not? Obviously, this model is completely random. But because you went through all the parameter combinations, there's 20 of those parameter combinations, just by chance, in one of those iterations, I tossed 62 heads. And the other experiments maybe included 50 or 45. So, typical distribution of randomness. If you do it 20 times, the best result, if you report the best result, that will obviously be better than the real accuracy of this model, which is pretty close to 50%, no matter how well I cost coins. All right, so how can this really ruin your business? So that's how I started, that machine learning and data science can really ruin your business. I think in a lot of cases, companies put models in production with very high expectations and very optimistic measurements on how well it will perform. So let's imagine a company which is losing 20 million because customers are leaving them, so the churn. For example, a telecom company, so if you're losing 500,000 users or subscribers every year, then probably all of them have like $40 value for you, then it's $20 million. So let's say you build a churn prediction model that tells you that if you do certain campaigns, then you can reduce it by 20%. So you're saving 4 million, they're not going to the competitor. It will be pretty good. But to achieve that, you need to spend some money. Maybe you need to give some discounts for these people, which costs you money. Maybe you give a new phone to these people. So that costs you like 2 million to gain that 4 million. But if your model is improperly validated, maybe the 20% improvement is only 5%. So you gained 1 million by spending 2. You are pretty much fired the next day. And it happens quite often. So people have pretty high expectations. Hey, this machine learning model will change the world. It will save so much money or generate so much new revenues for us. But all of these projects have inherent costs. So the cost of you building the model, maintaining this model, putting it into production, monitoring it, and maybe these costs of spending money on those customers who are likely to churn and giving them some giveaways to make sure they stay with you. So we have really seen companies going down, or at least analytics groups going down completely because of failed projects like that. So quick summary again, ignore training errors completely. So unless you are a very advanced data scientist, there it may have some value to you to understand how the model is converging and things like that. But for everybody else, just ignore it completely, no matter how good your model is on training data. You should always test it on independent test data. Use cross-validation, that's the easiest in most cases, or sliding window validation for time series like the stock market. And if you do optimization, always try to backtest with a new data set. So if you optimize on the same data over and over and over again, just by chance you will have a more optimistic outcome, a more optimistic estimate of your machine learning performance. And again, do not use information which is not available in production. That should be pretty straightforward, but I see so many projects being presented for business leaders with missing this, and it cannot never go into production because of that. So key takeaways again, correlations, be careful with them. Some of them are real, so obviously how machine learning models can predict things is looking into correlations and patterns. But if correlations are too strong, be suspicious. There might be something there. Cross-validation, and in general, I think a lot of people just jump on the train. When they hear deep learning, hey, let's buy GPUs, let's build the latest deep learning model. But hey, let's just use common sense and try to build attributes and generate new features which may be beneficial for the model, and not just brainlessly use whatever is hyped this week. And if you like, you can use RapidMiner for all this, but you do not have to. You can find all the tools in Python and R and with other tools to achieve these best practices. And regarding all this talk, much of the credit goes to my colleague Ingo Mirswa. He's a really fun guy. I really encourage everybody to search YouTube for 5 minutes with Ingo. He's having these crazy videos, which is partially fun, partially educational. So he's talking about machine learning topics with guest stars like Gandalf and the Unicorn. So yeah, please check that out. And thanks for your attention.
Thank you very much. Anybody has a question to the presenter? Thanks a lot for the presentation. I just was wondering which is the value of RapidMiner against the other R or Python environments. Is there any real value in using an established platform, an analytics platform?
I have to admit I'm not objective now, potentially. I'm biased. I think the value is that you can prototype much faster. So if you need cross-validation, or some optimization, or just putting together this visual workflow is typically much faster than coding it up in R and Python. Also, some of the restrictions you have in this visual interface stop you from making certain mistakes, which you can certainly do in any coding language. And also just the fact that some people have an easier way of understanding what you did if they see something visual and not a bunch of code. So especially like managers, business leaders, they have zero chance to understand an R code, but they have some chance to understand these visual workflows. So I think that's certainly a benefit. I can say even more and more, but I'm not a sales guy, so I will just, if you're interested, I can hand you over to somebody who can talk 1 hour about this.